Martingale and interaction. We know how to deal with a set of random variables, and in most cases we assume, almost all cases till now we assume that they are independently distributed, or in most cases independently and identically distributed. The most important thing is the independence of random variables. So, while studying this, all these theorems, results, lemmas, whatever with respect to this set of independent random variables or a sequence of independent random variables, now the question might arise that is it possible to discuss or study just relaxing this assumption? So, that means can we think of a set of random variables which are not dependent? Now, the question is, whenever we say that two variables are not independent, that means they are dependent, then the natural question would be, the most important question would be, what is the dependent structure? Now, there are various dependent structures, many structures are possible. So, today we are going to discuss one such structure that involves expectation of sequence of random variables, but having a particular dependent structure. Now, obviously this dependent structure is not very general, but a particular form, although this happens very frequently in real life. So, this important concept we call it as Martingale. So, today I will give you a very brief introduction on this Martingale and discuss a few examples and various elementary properties of this Martingale. So, the main objectives of today's talk, I will first introduce the concept, how it comes, few very basic results, and I will also at the end discuss two very interesting examples. So, the question is how this Martingale comes into the picture or into the area of probability theory. So, Martingale theory, like probability theory, has its origin in gambling theory. So, we all know that probability theory actually evolves. So, the main object of today's talk, I will first introduce the concept of Martingale, what is the meaning of this, how it comes, few very basic results, and I will also at the end discuss two very interesting examples. So, the question is how this Martingale comes into the picture or into the area of probability theory. So, Martingale theory, like probability theory, has its origin in gambling theory. So, we all know that probability theory actually evolves from a particular problem in gambling theory. The same way Martingale also has its origin in the gambling theory. The name Martingale is first used by Ville in 1939, but it was observed that it was known that Bernstein, Levy, they have already used this idea of Martingale, but they did not give any name to this particular phenomenon. So, let us first introduce this Martingale from a particular gambling, maybe from a gamble or a problem from the gambling theory. So, let us consider that xn be the fortune of a gambler after n trials in succession. That means after n trials, so a gamble means you are considering a gamble with one trial one after another. So, after nth trial or after n trials, the fortune of a gambler or the profit or the gain of the gambler is denoted by xn, which is naturally a random variable. Now, if a gambler survived the first n trials, so gambler's expected fortune after n plus 1 game should be expectation of xn plus 1 given fn. Now, script fn is a sigma field generated by the first or fortune in the first n trials, that is x1, x2, xn. Now, xn plus 1 is the fortune of the gambler after n plus 1 trials. So, the expected value is nothing but his expected profit or expected fortune. Now, we say that the game is fair if expected gain on trial n plus 1 is equals to 0, because expectation of xn plus 1 minus xn. So, xn plus 1 is the fortune after n plus 1th trial. Conditioning on this on fn, if we have xn minus xn, because we know that his fortune is xn. Now, after n plus 1th trial, if the expected fortune is xn itself, then only the expected gain would be 0. So, we can write immediately that expectation of xn plus 1 given fn equals to xn. So, under this condition we say that the game is fair. So, now when we say that the game is favorable to the gambler, if expected fortune is greater than xn, that means game is favorable if expectation of xn plus 1 given fn is greater than equals to xn, and it is unfavorable to the gambler naturally if expectation of xn plus 1 given script fn is less than equals to xn. So, one interesting observation that immediately appears from this points is that expectation of xn plus 1 given the sigma field generated before that, if this is equals to the variable that is observed at the previous trial, that is xn, that means xn, the value or expected value of xn plus 1 only depends on the previous random variable or the previous observation, and not the other observations before that, or not other past observations. Another thing is that if we can interpret this equality term here, we can also interpret if the equality changes to inequality. That means, in this case the game is favorable if it is greater than equals to, and if it is unfavorable if the expectation of xn plus 1 given fn is less than equals to xn. So, two important things are there. One is, not only we will discuss the equality situation, we should also concentrate, or we should also keep our mind open while in incorporating or in discussing what happens when this equality not holds. That means, what happens if there is some kind of inequality, and n plus 1th or observation or expected value on n plus 1th random variable should depend on the observed value of the at the nth trial. Another important thing is that this entire, so there is a dependent setup, dependent structure. So, x plus happening in n plus 1th trial depends something related to the previous trial or the nth random variable. And another important observation, or rather the most important observation, is that this dependent structure is through expectation, or rather conditional expectation. So, this simple gambling problem gives us a nice idea about a dependent structure involving random variables at one stage and random variable at the previous stage, but not other past stages, and this dependence is through the conditional expectation. So, this is very important. So, these are the observations. That means, xn plus 1 depends somehow on xn. That means, this is the first time we are deviating from the standard independence concept or standard IID random variables concept, and the form of this dependence is through expectation, rather conditional expectation. Now, let us formally define this situation, and while defining a random variable or conditional expectation, we should start with a probability space, which in this case is omega, script f and p, where script f is the sigma field generated by the class of subsets of omega, and p is the probability measure defined on the measurable space omega and script f. And let us consider xn as a sequence of random variables on this probability space omega, script f and p, and this is very important. And consider script f1 is a subset of script f2, is a subset of script f3, and so on. That means, we consider script fi I greater than equals to 1 as an increasing sequence of sub sigma fields of script f. Now remember, all these sigma fields are coming, sub sigma fields are coming from script f. Now if these three conditions hold, like if xn is fn measurable, that means xn is measurable with respect to the sigma field generated up to that point. So xn is therefore measurable. Expectation of mod xn less than infinity and expectation of xn given fn minus 1 is xn minus 1 almost surely. Then we call xn script fn is a Martingale sequence. So whenever we define a Martingale sequence, it is important to mention the sigma field, underlying sigma field, otherwise this entire thing has no meaning at all. So that means the sigma field or the sequence of sub sigma field associated with the sequence of random variables will be called Martingale sequence if these conditions hold. So in short, we will say that expectation of xn given script f n minus 1 equals to xn minus 1 almost surely, then we call this as a Martingale. If this conditional expectation of xn given fn minus 1 is greater than equals to xn minus 1 almost surely, we call it as sub-Martingale, and if it is less than equals to xn minus 1 almost surely, we call it super-Martingale. So we give names to all the situations whether there is equality or inequality. In fact, both types of inequality have different meanings, sub-Martingale and super-Martingale. Let us consider a few results. First result is that let xn fn be a sub-Martingale. So let us, it is important to note we start the result with a sub-Martingale sequence, not a Martingale sequence. So if xn fn be a sub-Martingale, g is a convex increasing function, then if gxn is integrable for all n greater than equals to 1, then gxn fn, this pair, is a sub-Martingale under the condition that g is a convex increasing function and xn fn is a sub-Martingale. In particular, xn plus is a sub-Martingale if xn is sub-Martingale. So this generalizes, this actually generalizes or provides us a very important class of sub-Martingales from one sub-Martingale, or rather we can construct several sub-Martingales from a class of, from a given sub-Martingale just by considering several convex increasing functions. Now we are going to state one theorem that is related to Martingale. So let xn fn be a Martingale. G is a simple convex function, not necessarily increasing, just a convex function. If gxn is integrable for all n greater than equals to 1, then gxn fn is a sub-Martingale. This is very important. We have started with this Martingale, but when we consider the convex combination, convex function, gxn fn is a sub-Martingale. In particular, for r greater than equals to 1, xn is a Martingale and modulus of xn to the power r is integrable, then modulus of xn to the power r is sub-Martingale. We are not going to prove this results because this is very trivial and very elementary proof, just follows from Jensen's inequality. We have already described Jensen's inequality for conditional expectation. So just application of Jensen's inequality along with the definition of sub-Martingale and Martingale gives us the proofs of these two results. Now just to give a feeling, I will discuss two examples. The first example is a famous one. We are encountered with this kind of a problem in probability theory, which is known as Polier's-Urn scheme. It says that suppose an urn contains R red balls and B black balls. Consider the proportion of black balls at the very beginning. That means put T naught equals to B by B plus R. Now at each drawing, the scheme goes like this. At each drawing, a ball is drawn at random, its color is noted, and a ball of same color is added to the urn. That means at the first draw, if we draw a black ball, then we add another black ball of the same color. We can generalize this by adding a number of balls of same color to this arm. That means if the first drawn color is black, then we add a number of black balls in the arm, so that during the next draw the number of black balls will be b plus a and the total number of balls will be b plus r. But if we have drawn a red ball, we should have added a number of red balls to the arm, so that the number of red balls would be r plus a and the total number of balls should be b plus r plus a. Now let us denote by Bn and Rn as the number of black balls and red balls respectively after nth drawing. Then show that Tn is martingale. How to prove this? The proof is extremely simple. All we have to show that expectation of Tn given Tn minus 1 is Tn minus 1. Now we know that probability of drawing a black ball at the n plus 1th draw depends only on balls in the arm after n drawings. Therefore, we immediately have expectation of Tn given Tn minus 1, Tn minus 2 up to T1 is nothing but expectation of Tn given Tn minus 1, because all the information contained in T1, T2 up to Tn minus 2 are incorporated within Tn minus 1, conditioning on Tn minus 1. So expectation of Tn given Tn minus 1 up to T1 is nothing but expectation of Tn given Tn minus 1 almost surely. Now let us calculate this expectation. So expectation of Tn given Tn minus 1 equals to Bn minus 1 by Bn minus 1 plus Rn minus 1, because after n minus 1th draw, number of black balls is Bn minus 1 and number of red balls in the arm is Rn minus 1. Now given that this is the situation, then expected proportion of black balls in the arm after nth draw should be equals to Bn minus 1 plus a by Bn minus 1 plus a plus Rn minus 1 into Bn minus 1 by Bn minus 1 plus Rn minus 1 plus here Bn minus 1 by Bn minus 1 plus Rn minus 1 plus a into Rn minus 1 by Bn minus 1 plus Rn minus 1. This is just using the simple elementary properties of probabilities and expectations. And if we just simplify this quantity, this entire quantities, then we will immediately see that we get Bn minus 1 by Bn minus 1 plus Rn minus 1, which is nothing but Tn minus 1. So we see that expectation of Tn given Tn minus 1 equals to nothing but Tn minus 1. So we can say that Tn is a martingale sequence. So the standard Polier-Zahn scheme that we know from the probability theory or some while working out some classical problems in probability theory, we see that this can also be observed or interpreted as a sequence as a martingale sequence. Let us consider another example which is directly related to or using a particular random variable. So we all know, we are familiar with the normal distribution. So let us consider yn to be a sequence of IID independently and identically distributed normal 0, 1 variables. Now Sn, if we define Sn equals to summation k equals to 1 to n yk, then naturally sequence Sn is not independently distributed, or the Sns for different values of n are not independent really. And we define xn alpha equals to e to the power or exponential alpha Sn minus n alpha square by 2. It is immediately clear that this xn to the power alpha or in xn upper alpha, this sequence is not independent for different values of n. Then we have to show that sequence of xn alpha is a martingale. The proof is very simple. Simple algebra will give us the proof. Let us mention that or describe expectation xn alpha given xn minus 1 alpha equals to expectation of, now what is xn alpha? This is nothing but exponential alpha Sn minus n alpha square by 2, conditioning on xn minus 1 alpha. Now we can easily split this Sn as Sn minus 1 plus yn, because Sn is nothing but y1 plus y2 plus yn minus 1 plus yn, and the first part is y1 plus y2 plus yn minus 1 is Sn minus 1. So we can immediately write it as alpha Sn minus 1 plus alpha yn given Now, just I am writing for the sake of simplicity that x n minus 1 alpha is nothing but exponential alpha s n minus 1 minus n minus 1 alpha squared by 2, and just a little bit of manipulation will give us expectation of alpha s n minus 1, because conditioning on s n minus 1, this s n minus 1 is constant. So, we can keep this outside the expectation, into expectation of e to the power alpha y n given something that is related to up to variables up to n minus 1. Now, since y n's are IID, so naturally y n and y 1, y 2, y n minus 1, and hence y n and s n minus 1 are independent. So, this condition we have learned a sequence of random variables which are not independent. That means there is a dependent structure which we call Martingale. So, this particular dependent structure is called Martingale. We have already studied. We have already studied a few examples and one or two results that are related to this Martingale sequence of random variables. Now, it is important to note at this point that although we have devoted only a few minutes to this Martingale theory, it is basically an introduction. I am trying to just give you a feeling of what this Martingale is and how one can use, and how some very common problems can be looked upon as a consequence of Martingale theory. Naturally, one can do a lots of research, and lots of research have already been done in this area, and still research is still moving on in this area of Martingale sequence of random variables, and naturally one can extend this idea. That means one can think of some other dependent structure that is possible in case of some dependent random variables, or a sequence of random variables which are dependent. But today we only confined our attention only to Martingale sequence.